Okay, so we started this whole thing off with some geometric conditions, and we wanted to know what kind of curve does it make if you fill in all the points that are exactly the same distance from this point and that line. And so we thought about it. We said, okay, well, clearly the point that's, exactly halfway between the point and the line, that's going to be a point on our curve. And then as I move away from P down, it seems like I'm going to have to move towards P in this direction. And so we sort of sketched it out, and it sort of seemed like it was going to end up being a parabola. But we weren't totally sure. And so we decided to derive it algebraically. So we described a distance 1 and a distance 2 to an arbitrary point xy on the curve that we think exists. So here's xy, and we called this distance 1 and this distance 2. And then we said, what curve do you get if you set distance 1 equal to distance 2? And we had equations for those, and it ended up being a parabola, just kind of like we thought. So mathematicians like to generalize. And so we might start with a different set of conditions. What if the two distances don't have to be the same? What if distance 2 is always twice as big as distance 1? In other words, let's figure out what distance 1 is going to be, and then let's multiply it by 2, and that's how far the point has to be from the line. That's distance 2. So thinking about it that way, we're going to have to sketch in a new curve. And in fact, why don't you pause the video right now and decide, where does this point have to be if distance 1 is twice as big, if distance 2 is twice as big as distance 1? Where does that point move to? And then what do the other points maybe look like? Just make a guess. Okay, well, so here's my guess. If distance 2 is twice as big as distance 1, it means that that distance here has to be twice as big as that distance there. So, in other words, this point is now 2/3 of the way between this line and the point P. I think that makes sense. But just like we had before, it seems like as we're going this way, we also have to go that way in order to keep this distance large enough that it's going to be twice as big as D1. So it still seems like maybe we're getting a parabola. So like maybe, I'm making a conjecture here, maybe this is some type of scale factor. But, all of this is very hand-wavy and intuitive, and your intuition can go wrong. So let's do the same thing we did last time. Let's try and verify it algebraically by making equations for D1 and D2, and then seeing how the derivation comes out. All right, so D1, so this is, all right, let's fill in some points here. So we know this is the line x equals 1. We know this is the point 4, 0. This is an arbitrary point x, y. So this distance is going to be possibly a diagonal line, and so we're going to use the distance formula. So let's see. Let's do x minus 4 squared. That's the difference in x's. And then y minus 0 squared. Well, it's a little silly to write y minus 0 squared, isn't it? So let's just write y squared. Okay, so that's distance 1. So distance 2 is going to be this horizontal line. Let's figure out what that should be. So I know from here to there it's distance 4, and from here to here, wait, what am I trying to do? Okay, so from here to here it's distance x, correct? So here to here is distance x, and I know from here to here is distance 1. So this remaining distance in the red must be x minus 1. Okay. So let's go ahead and square both sides and see what we end up getting. And in fact, why don't you go ahead and get this as far as you think you can, remembering what you did last time. So go ahead and pause the video. I'm going to do it too. All right. So I squared both sides. The square root got undone, and the 2 became a 4 when I squared it. And this side squared, of course. Then I distributed the 4 in, so I've got 4 times this first term plus 4 times the second term. What I'm hoping to do now, I see I've got 2 different x squared terms on opposite sides. So let's not touch the y. In fact, there's really nothing to do with the y. Let's expand these 2 and see what cancels, just the same way that we did last time. So here I've got 4 times, I'm going to expand this now, so x squared minus 8x plus 16. And then that's the same. And then here I've got x squared minus 2x plus 1. All right, and I guess let's distribute the 4 in. So 4x squared. What was I doing? Oh yeah, 32x. All right, and then 4 times 16. And if you don't know what 4 times 16 is, well, here's one easy way to think about it. So like multiply 4 by 2 and divide 16 by 2, right? If you're affecting both of these by the same amount, they should sort of cancel each other out. So 4 times 2 is 8. 16 divided by 2 is 8. So 4 times 16 should be the same as 8 times 8. Or if you want to, there's no reason not to just leave it like this. Because, maybe later on we're going to have something that cancels. So you can just leave this as a single number, 4 times 16. Okay, what am I missing here? So we've still got the 4y squared here. And then everything else is the same. Okay, so now something's very different about this than all the situations we've had before. In all the situations we've had before, there was a term on both sides, like either a y squared or an x squared, where there was the same number. So we'd like subtract y squared from both sides, and we'd eliminate that from the equation. Or we'd subtract x squared from both sides, and we'd eliminate it. But here, there's a different number of x squareds on each side, and there's a different number of y squareds on each side. Here there's 4, here there's 0. So what that tells me is it's not going to be possible to eliminate an x squared or a y squared. So we can't be aiming for like y equals something or x equals something. Or I guess we could. But I think what I want to do instead is let's just collect everything on the left-hand side and try and group the x squareds and the y squareds. All right, so let's subtract an x squared from each side. So x squared from 4x squared gives us 3x squareds. Let's add a 2x. So if I have negative 32 plus 2, that's going to be negative 30x. Okay, so we've taken care of those. Let's subtract a 1. Or actually, let's move the constant over to the other side. So here we'll have 1 minus 4 times 16. So taking care of those ones. And then here we've got 4y squared. Okay, so far so good. So we've got all the variables on this side, and we've got constants on this side. I guess let's maybe go ahead and make this just negative 63, which is what it is. So I hope that this right here is screaming out at you for simplification. You might be tempted to do this, 3x times x minus 10. And that would definitely be a way you could factor it. But that's not the way of factoring it that's going to tell us the most. I think it's going to tell us the most if we actually complete the square. So let's complete the square on it instead. There's nothing wrong with starting off by factoring out the 3, though. So let's factor out the 3. Okay, and now let's complete the square. So here on the inside, I've got x minus 5 squared. And so let's think about this. If we're going to expand this, we got the x squared. We've got the minus 10x. But this is going to introduce an extra plus 25 in that last term. So we got to subtract 25 in order to compensate. And now I think, so now we have this extra ugly constant. So let's redistribute the 3 so that we can get this constant over to the other side. Because I really like to have all the variables on one side and all the constants on the other side. All right, so let's redistribute. We've got 3x minus 5 squared. And then this is now minus 75 because 3 times 25 is 75. Okay, so now let's add 75 to both sides. And finally, we will have, let's see, so 75 minus 63 is what? 63, 73, so this is going to be 12. And then here we've got 3 times x minus 5 squared plus 4y squared. Okay, very interesting. So I don't know why I put a box around it. I mean, we can keep doing things with it. What does this mean? right? We started over here. We just made a small change. We just said distance 2 is now twice as big as distance 1. We thought about it. It seems like it's still shaped like a parabola, but then when we did the algebra here, this does not look like the equation for a parabola. So clearly this is telling us something. So come back in the next video and we'll try and interpret what does this equation tell us about the actual curve. And you might have some guesses.